This is where they are building the largest nuclear fusion reactor in the world.
These results are really significant because what we've managed to demonstrate inside JET is that we can create a mini sun, the right kind of mini sun, hold it there for a sustained period and get really good performance levels.
Nuclear fusion, the energy source that powers stars, has long been a dream for scientists. It promises near unlimited clean energy with minimal waste. But achieving this dream has proven elusive. Now, a recent breakthrough in Germany involving a powerful experimental machine has reignited hope. Could this be the game changer that finally unlocks the potential of fusion energy? Are we on the cusp of a new era of clean and abundant power? Harnessing the power of the stars, throwing a pebble and getting a whole boulder back with even more energy to spare might sound like science fiction. But that's the basic idea behind nuclear fusion. It's the opposite of what happens in the nuclear power plants we use today. Instead of splitting atoms to release energy, like in nuclear fission power plants, fusion smashes them together to create even more energy. If we can unlock the secrets of making fusion work on Earth, it could solve our energy problems forever. Imagine a world where our energy needs are met by a virtually limitless source that's clean, safe, and affordable. That's the promise of nuclear fusion. Compared to nuclear fission, fusion boasts a staggering output. It could generate 4 times more energy per kilogram of fuel. That's like getting 4 times the mileage out of a single tank of gas in your car. And that's not all. When compared to burning fossil fuels like oil or coal, fusion is a powerhouse, generating nearly 4 million times more energy. This isn't some far-off fantasy. Our very own sun is a giant ball of fusion, constantly merging hydrogen atoms into helium. This is the source of its immense heat and brightness. Scientists are essentially trying to build miniature suns here on Earth to generate clean and powerful energy. But it's not as simple as tossing a couple of hydrogen atoms together. Fusion requires an exotic state of matter called plasma. Think of it as a superheated gas so hot that its atoms are ripped apart into positively charged cores and free-floating electrons, creating a swirling soup of subatomic particles. This plasma is completely different from the solid, liquid, or gas states we normally encounter. Let's take a trip to the center of our sun to understand the process better. To ignite fusion, hydrogen nuclei in the sun's core need to collide at unimaginable temperatures, around 10 million degrees Celsius. That's hot enough to vaporize any spacecraft we have ever built. Why such extreme heat? At these temperatures, the hydrogen nuclei gain enough energy to overcome their natural repulsion, like 2 magnets trying to push each other away. But once they get incredibly close, a different force takes over, the strong nuclear force. This force acts like a superglue, binding the nuclei together and releasing a tremendous amount of energy in the process. However, for this to happen consistently, we need to confine all these speeding nuclei in a small space. In the sun, gravity does the job. The sun's immense weight creates incredible pressure, forcing the nuclei close enough to interact. Germany's quest for clean energy supremacy. The dream of harnessing the power of the stars on Earth has captivated scientists since the 1930s, when the theory of nuclear fusion first emerged. Now engineers are joining the quest, driven by the potential of replicating this process and using it to generate clean energy on an industrial scale. However, the road to achieving this clean energy utopia is paved with significant scientific and technical challenges. There is still much to be learned about the intricate workings of fusion, and the hurdles to overcome are substantial. Despite the immense difficulties, the potential rewards are so vast that countries like Germany are pouring billions of dollars into fusion research. The German government, for instance, is firmly committed to unlocking the potential of fusion energy. They have launched a dedicated funding program called Fusion 2040, Research on the Way to a Fusion Power Plant. This ambitious initiative aims to create Germany's first ever fusion power plant by the year 2040. Safe, clean, and limitless. Unlike traditional nuclear fission reactors, fusion reactors wouldn't rely on the heavy elements like uranium or plutonium. that come with a host of safety concerns. The fuel for fusion is much simpler. The most common approach uses a blend of two special types of hydrogen, deuterium and tritium. These are essentially hydrogen atoms that have one or two extra neutrons in their nucleus, respectively. The beauty of this fuel source is that it's incredibly abundant and easy to get. Deuterium can be practically extracted from seawater for free. Tritium is a bit trickier, but even that can be produced within the reactor itself. Here is how it works. The neutrons released during the fusion reaction can be used to bombard naturally occurring lithium, another element found in abundance. This bombardment converts some of the lithium into tritium, creating a self-sustaining fuel cycle within the reactor. Imagine the potential. With just a few grams of this fusion fuel, you could generate a terajoule of energy. That's a huge amount of power, roughly equivalent to what a person in a developed country uses in their entire lifetime. Even better, these fuel sources are estimated to last for millions of years, providing a practically endless supply of clean energy. The beauty of fusion fuel goes beyond its abundance. It also offers significant safety advantages. Unlike traditional nuclear fission reactors, fusion doesn't produce the same kind of dangerous, long-lasting radioactive waste. Additionally, the nature of fusion itself makes runaway reactions and meltdowns highly unlikely. Why? Because fusion only occurs under very specific and controlled conditions, extreme temperatures and pressure. If there is any disruption to the carefully controlled environment within the reactor, the fusion process simply stops. The plasma cools rapidly, losing its energy and essentially fizzling out before any damage can be done. This inherent safety feature makes fusion a very attractive prospect for a clean and sustainable energy source. The fight against climate change hinges on finding clean and sustainable energy sources. Nuclear fusion offers a powerful solution in this fight because, like nuclear fission, it produces no greenhouse gases or harmful carbon dioxide emissions. Nuclear crossroads. Now, it's important to understand the difference between fusion and the current nuclear fission technology used in power plants since the 1950s. As mentioned before, fission reactors work by splitting atoms, releasing a tremendous amount of energy in the process. This established technology has its advantages. Over 400 fission reactors are currently operating around the world, providing a reliable source of electricity. However, fission also comes with safety concerns. While nuclear disasters are thankfully rare, incidents like the Chernobyl meltdown in 1986 serve as stark reminders that fission power isn't entirely risk-free. Radioactive waste disposal from these reactors is another significant challenge. Germany's decision to shut down its last remaining nuclear power plants in 2023 is a case in point. This move, often seen as a reaction to the Fukushima disaster in 2011, was actually part of a much larger energy transition plan called the Energiewende, deeply rooted in German society for many years. The Energiewende aimed to shift the country towards renewable energy sources like wind and solar, while also phasing out nuclear power due to the safety concerns it raises. Germany's nuclear energy revolution. Germany's journey away from nuclear power has a long and complex history, fueled by a combination of public concern and political action. Anti-nuclear movements began to take root in the 1970s, with local communities springing into action. These weren't just isolated pockets of resistance. Protests and legal challenges against specific nuclear power plant projects gained widespread support across party lines. In 1975, this public opposition reached a turning point. A massive demonstration of 28,000 people occupied the construction site of a planned nuclear plant in Well. Their determined action managed to halt the project altogether. This was just the beginning. The accident at the 3 Mile Island nuclear power plant in the United States in 1979 sent shockwaves across the Atlantic. In Germany, the disaster served as a wake-up call. Around 200,000 people took to the streets in major cities like Hanover and Bonn, demanding a shift away from nuclear energy. These large-scale demonstrations weren't isolated incidents. Wherever plans arose for radioactive waste processing or storage facilities, protests erupted, reflecting deep public unease about the long-term consequences of nuclear technology. Then came the Chernobyl disaster in 1986. This catastrophic meltdown in Ukraine unleashed a wave of fear across Europe, and Germany was no exception. Public sentiment against nuclear power soared, with a majority of Germans expressing deep concern about the safety risks. This shift in public opinion had a profound impact on the political landscape. Politicians began to publicly acknowledge the limitations of nuclear power, calling it a transient technology, a temporary solution rather than a long-term answer. This shift was reflected in policy decisions. After 1989, no new commercial nuclear power plants were built in Germany. The public remained vigilant throughout the 1990s. Protests continued, particularly targeting the transportation of spent nuclear fuel, the leftover radioactive material from reactors. People voiced concerns about the safety risks associated with transporting this dangerous material to and from processing facilities and potential waste storage sites. These sustained demonstrations and public pressure played a significant role in shaping Germany's energy policy and its ultimate decision to move away from nuclear power altogether. Navigating the path to Fusion Energie. Germany's decision to phase out nuclear power, along with similar decisions by other countries, cast a spotlight on the need for alternative energy sources. Fusion research has gained significant momentum as a potential solution, but it's important to understand that we're still in the early stages of this journey. The first ever fusion reactions achieved in a lab back in 1934 were a monumental breakthrough. It proved the concept was theoretically possible. Today, it's interesting to note that achieving a basic fusion reaction isn't necessarily the most difficult part. In 2018, a remarkable young scientist, at just 12 years old, entered the Guinness World Records for creating a fusion experiment at home. This achievement highlights the relative accessibility of the basic principles. However, there's a crucial difference between a party trick and a sustainable energy source. The fusion reactions achieved in these small-scale experiments are like tiny fireworks, short-lived bursts lasting mere fractions of a second. The real challenge lies in replicating these reactions, not just once, but continuously and for extended periods. This is where the true scientific and engineering hurdles come in. We need to figure out how to create and sustain these reactions for long enough to generate a usable amount of energy. That's the missing piece that will unlock the true potential of fusion power. Balancing heat, pressure, and magnetic fields. While the sun uses its immense gravity like a cosmic pressure cooker to get fusion going naturally, here on Earth, it's a different story. Without that incredible gravitational force, we need to crank up the heat to even higher levels than the sun's core. That's hot enough to melt any material we know of, but just heat isn't enough. To get deuterium and tritium to fuse, there is a need to control the pressure and magnetic forces with incredible precision. Imagine trying to juggle fire while riding a unicycle on a tightrope. That's kind of what scientists are up against. The pressure needs to be immense, squeezing the fuel together like a subatomic mosh pit. At the same time, powerful magnetic fields are needed to confine this superheated soup of particles so as to prevent it from touching the walls of the chamber and losing its energy. The key is achieving a state called plasma confinement. In the end, the ultimate goal is to sustain this whole process, the extreme heat, the precise pressure, and the magnetic confinement for a long enough period. The fusion reaction must also become self-sufficient, producing more energy than it takes to keep it going. Taming Chaos. Even if we can achieve the mind-boggling temperatures and pressures needed for fusion, there's another hurdle to overcome. Keeping the plasma stable enough to extract usable energy is no easy feat. Imagine trying to control a swarm of angry bees while simultaneously extracting honey. That's kind of what it's like. Plasma is inherently chaotic. It's prone to turbulence and other instabilities that can fizzle out the entire fusion reaction. Understanding, modeling, and controlling this chaotic plasma is a scientific feat in itself. But researchers haven't been discouraged. Over the past few decades, they have made significant strides in this field. One way scientists manipulate plasma is with the help of magnetic confinement devices. These are essentially giant machines that use powerful magnetic fields to keep the charged particles in the plasma corralled. The two most common types of fusion reactors that use magnetic confinement are tokamaks and stellarators. These are currently considered the frontrunners in the race to develop practical fusion power plants. Both tokamaks and stellarators rely on a fundamental principle. Charged particles, like the ions in plasma, are highly responsive to magnetic forces. By strategically placing powerful magnets within the reactors, scientists can confine these ions. Electrons, though not the main players in the fusion reaction itself, are also influenced by the magnetic fields and contribute to the overall stability of the plasma. These magnetic forces essentially whip the particles around in a continuous loop within the donut-shaped chambers of the reactors. This constant motion keeps the plasma from escaping and ensures the particles collide frequently enough for fusion to occur. Tokamaks, stellarators, and the future. Both tokamaks and stellarators have their own strengths and weaknesses. Tokamaks, with their simpler donut-shaped chambers, are currently the workhorse of fusion research. Their simpler design makes them easier and faster to build, and around 60 tokamaks are currently in operation around the world, compared to just 10 Stellarators. This doesn't mean tokamaks are the undisputed champion, though. Each design offers unique advantages. Tokamaks excel at keeping the plasma hot, a crucial factor for achieving fusion. Stellarators, on the other hand, shine in terms of plasma stability. Their more complex, twisted coil configurations allow for a more relaxed plasma confinement, meaning the particles aren't constantly bouncing around like popcorn kernels in a hot pan. This translates to a steadier, more predictable environment for fusion to occur. Despite tokamaks taking the lead for now, the future of fusion energy remains an open field. Stellarators still hold promise, and continued research could one day tip the scales in their favor. This is where the awe-inspiring Wendelstein 7X reactor in Germany comes in. This machine is a stellarator unlike any other, a true game-changer in the world of fusion research. Let's delve deeper and explore the marvels of the Wendelstein 7X. Exploring the Wendelstein 7X, tucked away in Greifswald, Germany, lies the Wendelstein 7X reactor, a scientific marvel pushing the boundaries of fusion research. Completed in October 2015 by the Max Planck Institute for Plasma Physics, this isn't your ordinary power plant. The Wendelstein 7X is an experimental stellarator, a machine designed to unlock the secrets of fusion energy through a unique approach. As of 2024, it holds the title of the world's largest stellarator device. While it won't be generating electricity just yet, the Wendelstein 7X plays a crucial role in the grand scheme of fusion power. It's essentially a testbed, a powerful tool for scientists to evaluate the key components needed for a future fusion power plant. It is the successor to the Wendelstein 7AS, another experimental reactor that paved the way for this more advanced design. By meticulously studying how the Wendelstein 7X handles the challenges of plasma confinement and fusion reactions, scientists are gaining valuable insights that will ultimately help shape the future of clean energy. Inside the fusion core, the secret sauce behind the Wendelstein 7X lies in its unique design. Unlike tokamaks that use a simple donut-shaped magnetic field, the Wendelstein 7X takes a more sophisticated approach. It is based on a concept called a 5-field period Helias configuration. Imagine a complex braid of magnetic fields, carefully woven together to create a specific shape. That's essentially what this configuration is. This intricate braiding is achieved using a multitude of magnets. The Wendelstein 7X boasts of 70 magnetic coils. These coils, towering 3.5 meters high, are superconducting, meaning they operate at incredibly low temperatures to conduct electricity with minimal resistance. 50 of the coils are non-planar, and this means that they're not flat, but rather have a specially designed, twisted shape. This complex arrangement is key to creating the right magnetic field for plasma confinement. The intricate magnetic field serves a critical purpose of confining the plasma within the reactor chamber and preventing it from touching the walls. Remember, plasma is superheated and unruly, and the last thing you want is for it to come into contact with anything solid. The carefully designed magnetic field acts like an invisible cage, keeping the plasma contained long enough for fusion to occur. The Wendelstein 7X is also optimized along a principle called quasi-isodynamic. This essentially means that the forces acting on the plasma are balanced and evenly distributed. This helps to minimize instabilities within the plasma, keeping it nice and stable, a crucial factor for a sustained fusion reaction. Now let's take a peek inside this remarkable machine. The core components include, of course, the magnetic coils we just discussed. But that's not all. The Wendelstein 7X also houses a cryostat, which is essentially a giant thermos, keeping the superconducting coils at their ultra-cold operating temperatures. The plasma vessel sits at the heart of the machine where the fusion reaction takes place. There's also a diverter system, which plays a crucial role in managing impurities and heat exhaust within the plasma. Finally, heating systems are used to give the plasma an initial boost, raising its temperature to the millions of degrees needed for fusion to occur. To understand how well everything is working, scientists rely on a sophisticated network of sensors and probes. These high-tech tools measure various properties of the plasma, like the density and temperature of electrons and ions, the presence of impurities, and the electrical field within the plasma. This constant monitoring allows researchers to analyze the behavior of the plasma, identify areas for improvement, and ultimately optimize the fusion process. Now, it's time for today's subscriber pick. Recently in Germany, there has been a buzz in the world of fusion energy, and to make things even more intriguing, this image is circulating online with the caption, "Germany's new nuclear fusion reactor shocks the entire industry." The image itself looks like something straight out of a science fiction film. It features a man standing beside a giant donut-shaped machine with intricate metal coils wrapped around its surface. This behemoth could be a game-changer in the quest for clean energy. While the exact details surrounding this machine are a little fuzzy, it strongly resembles a stellarator, a type of experimental fusion reactor. Stellarators use powerful magnetic fields to confine superheated plasma, the key ingredient for fusion. If this breakthrough is real, it could signify a significant leap forward in achieving sustained fusion reactions. So, what do you think? Could this German breakthrough be the key to unlocking the potential of fusion energy? And what kind of impact might it have on the future of clean energy? Let us know your thoughts in the comments below. From concept to reality. At this point, let's explore the intriguing story behind the creation of the Wendelstein 7X reactor. The story of the machine is a fascinating journey of scientific ambition, international collaboration, and perseverance. The seeds of this project were sown back in 1994, when funding arrangements were established in Germany. This wasn't just about building a new machine, it was also about establishing a new branch of the Max Planck Institute for Plasma Physics in Greifswald, a city in the northeastern corner of Germany. The year 2000 saw the completion of a new building to house this ambitious project. Originally, the grand vision was to have the Stellarator up and running by 2006. Construction began in April 2005, and for a while, things seemed on track. However, the road to scientific discovery isn't always smooth. The team encountered challenges with the complex magnetic coils, crucial components for confining the plasma. These hurdles took a significant amount of time to overcome, pushing back the completion date to late 2015. Thankfully, the researchers weren't alone in this endeavor. A consortium of 3 prestigious American laboratories, Princeton, Oak Ridge, and Los Alamos, joined forces with the German team. This partnership involved a significant financial contribution of 6.8 million euros towards the project's total cost, which eventually reached 1.6 billion euros. Funding for the Wendelstein 7X came primarily from two sources, Germany and the European Union. Germany shouldered the lion's share, with about 80% of the total cost. The remaining 20% was funded by the European Union, demonstrating a united European front in the pursuit of clean energy solutions. Within Germany itself, the financial responsibility was further divided. The federal government covered 90% of the German contribution, while the state government of Mecklenburg-Vorpommern provided the remaining 10%. The year 2012 saw another exciting development. Princeton University and the Max Planck Society joined hands to establish a new joint research center specifically focused on plasma physics, with the Wendelstein 7X playing a central role in their collaborative research efforts. Finally, in May 2014, after more than 1 million assembly hours, the construction phase officially concluded with an inauguration ceremony. However, the work wasn't quite finished yet. The following months were dedicated to meticulous checks for leaks in the vessel, a crucial step before any experiments could begin. Once these checks were completed, the summer of 2014 saw the evacuation of the cryostat. By July 2015, magnet testing was complete, paving the way for the first plasma experiments in the coming months. Wendelstein 7X's Maiden Experiments. The year 2015 marked a historic moment for the Wendelstein 7X. After years of planning and construction, it was finally time to see if this scientific marvel could live up to its potential. On December 10, 2015, operational phase 1.1 officially began. It was the day the Wendelstein 7X fired up for the first time. This initial experiment wasn't with full power or complex fuel mixtures. The team started cautiously with helium plasma, a simpler gas to work with. Even with this basic fuel, the achievement was significant. The reactor successfully produced a helium plasma, with temperatures reaching around 1 million degrees Kelvin for a brief period of 0.1 seconds. To achieve this, they injected a tiny amount, about 1 milligram, of helium gas into the evacuated chamber of the Wendelstein 7X. Then, with a burst of microwave heating, they ignited the gas, turning it into a hot, swirling current of charged particles. The goal of this initial phase was to conduct a series of tests, ensuring all the critical systems were functioning properly. It was also a chance for scientists to gain valuable experience understanding how the physics played out within the machine. Over the next few months, they performed more than 300 similar experiments using helium. Gradually, they cranked up the heat, eventually reaching a scorching 6 million degrees Celsius. This extremely hot temperature served two purposes. It helped clean the walls of the chamber from any lingering impurities, and it allowed them to test the various diagnostic systems used to measure the properties of the plasma. Then, on February 3, 2016, a significant milestone was reached. They successfully produced the first ever hydrogen plasma within the Wendelstein 7X. This was a major leap forward, because hydrogen is the key fuel for fusion energy. The experiments with hydrogen plasma continued throughout the rest of the phase, with scientists gradually increasing the power and duration of each pulse. At its peak, the microwave heater pumped out 4 megawatts of power, sustaining the plasma for a full second. During these experiments, the electron temperatures within the plasma soared to a scorching 100 million degrees Kelvin, while the ions, the cores of the hydrogen atoms, reached a sizzling 10 million degrees Kelvin. By the time operational phase 1.1 concluded in March 2016, they had conducted over 2,000 successful pulses, collecting a wealth of data for further analysis. One interesting aspect of this initial phase was the use of temporary components. Instead of the final design that would be used for long-term operation, they used temporary graphite limiters to manage the edge of the plasma. These limiters acted like bumpers, preventing the superheated plasma from touching the walls of the chamber. Experimental observations during this phase confirmed the accuracy of complex 3D models that predicted how heat and particles would flow within the plasma. With this successful first phase complete, the Wendelstein 7X was ready for an upgrade, reaching new heights. After the successful initial tests of operational phase 1.1, the Wendelstein 7X wasn't done yet. In 2017, it entered operational phase 1.2. This new phase had a specific goal to thoroughly test the diverter, which, as we mentioned before, is crucial for managing impurities and heat exhaust within the plasma. Operational phase 1.2 focused on putting this crucial component through its paces, ensuring it could handle the heat and particle flow within the reactor. By June 2018, they had achieved some record-breaking milestones. The ion temperature within the plasma reached 40 million degrees. They also managed to squeeze in a high density of particles 8/10 times 10 to the power of 20 particles per cubic meter, and maintained a descent confinement time of 0.2 seconds. These factors combined to produce a record-setting fusion product 6 times 10 to the power of 26 degree seconds per cubic meter. In simpler terms, this meant they were getting more fusion reactions happening per unit volume within the plasma. As 2018 drew to a close, the achievements continued to pile up. They managed to push the particle density even higher while maintaining a temperature of 20 million degrees. This sweet spot allowed them to achieve longer, more sustained pulses of plasma, lasting up to 100 seconds. The total energy content within the plasma even surpassed 1 megajoule, demonstrating the potential for this machine to pack a serious punch. Fast forward to 2021, and scientists were still analyzing data collected during those record-breaking 2018 experiments. Using a special X-ray imaging crystal spectrometer, they discovered something fascinating. Earlier predictions suggested that collisions between the superheated particles within the plasma would cause some of them to escape the magnetic field, leading to heat loss. However, the data revealed a surprising truth. Thanks to the optimized magnetic field cage design, they were able to significantly reduce this troublesome heat loss. In essence, the Wendelstein 7X's intricate magnetic configuration was proving to be even more efficient than initially expected. Chasing continuity. The Wendelstein 7X, after 2 successful periods of operation that concluded in October 2018, the reactor went offline for crucial upgrades. The upgrade process, completed in 2022, aimed to refine the machine's capabilities. New experiments conducted in February 2023 marked a significant leap forward. The upgraded machine achieved 2 key improvements: longer plasma confinement and increased power output. Plasma confinement, remember, is essentially how long the superheated gas can be held within the magnetic cage before it touches the walls and cools down. Extending this confinement time is critical for a successful fusion reaction. But the goal goes beyond these impressive achievements. The current phase of operation has a singular focus, gradually increasing the power and duration of the plasma discharge. The ultimate target is to achieve a continuous plasma discharge lasting 30 minutes. This feat would be a major breakthrough, demonstrating a critical feature for any future fusion power plant: the ability to run continuously, not just in short bursts. If the Wendelstein 7X can achieve this feat, it would be a significant validation of the Stellarator approach to fusion energy. It would pave the way for even larger and more powerful Stellarators in the future, bringing the dream of clean and abundant fusion power a step closer to reality. Thanks for watching. See you in the next video.